Okay, so we derived the equation, we derived the expression for the thermal conductivity of matter. This is the thermal conductivity, and then we talked about the Lorentz number, we talked about the Wiedemann-French law. Now we are going to talk about very important topic of this chapter, Hall effect. Hall effect. So you have you may also have studied this topic in your earlier classes. So you know that if a conducting material is kept in a uniform magnetic field and a current is passed along the length of the conductor, a voltage is found to develop at right angle to both the direction of the current as well as the direction of the magnetic field, right? So the voltage produced as a result of this impact of the electric field as well as the magnetic field is known as the Hall voltage, right? So we can say that if the current, if the electric field is applied along x direction and if the magnetic field is applied along the y direction, then a voltage is produced along other perpendicular direction, third perpendicular direction, which is the z direction, right? So if the electric field is along x and if the magnetic field is along y, then Hall voltage will be produced along z direction. Okay, so let us see what is the origin of this Hall voltage, right? How does the electric and magnetic field both impacts the charge carriers inside the metal so that the Hall voltage is produced. Okay, so let us consider a piece of metal, let's say specimen. So this is a specimen in the form of rectangular cross section, and this is carrying current Ix in the x direction. Let's say this is the x direction. So this is carrying current along this direction, Ix. Now, if a uniform field is applied, let's say along z direction, if we apply, let's say this is the three-dimensional system. So this is the x direction and hence this is the direction of the electric current. And let's say if the magnetic field is applied along this direction, let's say z direction, then a Hall voltage will be produced in y direction, denoted by Vh. So it is found that an EMF is developed along the y-axis, and due to that EMF, a voltage is generated, a voltage is produced, which is perpendicular to the direction of the electric and magnetic field. Okay, so let us understand what is the origin of this Hall voltage, why this field is generated and how it is generated. Okay, so let us first consider the situation when there is no magnetic field. That means that we have applied only the electric field and there is no magnetic field applied on the specimen. Okay, so under the influence of the electric field, the conduction electrons are drifting with a velocity, let's say Vx, along the negative x direction. So if this is the positive x direction, this will be the negative x direction. So if the field is applied along positive x direction, then the electrons will be drifting along negative x direction, right? So this will be the flow of the electrons. The electrons will be flowing in this direction. Okay, now what happens when we apply magnetic field to this specimen? Another force, which is known as the Lorentz force, will cause the electrons to bend downwards, right? So these electrons will experience a force which is FL, which is Lorentz force. Lorentz force is the combination of the electric field as well as the magnetic field, you know that, right? So as a result, these electrons will experience a force, and as a result, they will go downwards. Okay, so they will move downwards. So as a result, the electrons accumulate on the lower surface. As a result, there will be accumulation of the electrons on the lower surface of the specimen, right? And as a result of more concentration of the electrons downwards, there will be a positive charge developed on the upper surface of the specimen, right? So due to this separation of the charges, an EMF is developed inside the specimen, and due to that EMF, this Hall field is induced. So this EH is known as the Hall field. This is known as the Hall field. Okay. So now we know that, now you understand the situation. What is the origin of the Hall field, how it is generated. You might have done this experiment in the laboratories in your previous classes, and then you might have calculated the value of the Hall field as well as the Hall voltage, as well as the Hall coefficient, mobility, free charge concentration. So basically the purpose of this experiment, or the purpose of doing this experiment in the laboratories is to find out the concentration of free electrons, to find out the mobility of the charge carriers, to find out the Hall coefficient. So all these things, even that we can also determine the sign of the charge carriers, whether they are holes or whether they are the electrons. It can be determined by using this experiment. So this is very important experiment in physics. Okay. So let us start with the Lorentz force. We know that Lorentz force FL, Lorentz force FL is given by E Vx Bz. Okay, the field created by the surface charges produces a force which opposes this Lorentz force. Okay, so this Lorentz force is the external force, right? This is the combination of the electric plus magnetic field. So this is the external force, right? But due to this external force, a Hall voltage is being generated inside the specimen, right? And this Hall voltage, or this force which is generated due to this potential difference, will oppose this Lorentz force, right? And in steady state, this Hall force, which is internal force, must be equal to the Lorentz force. So it means that now we know that this Hall force is given by EH, right? Force is equal to charge into electric field, and this is equal to Lorentz force. Lorentz force is E Vx Bz. So EH is equal to Vx Bz. Let us say this is equation number 1. We also know that the current density Jx is given by minus NeVx, where negative sign denotes that the electrons are drifting opposite to the applied field. Okay, so let us say this is equation number 2. Let us divide equation number 1 by equation number 2. So dividing 1 by 2, we get EH by Jx is equal to minus Bz divided by Ne. Okay. Uh, so you can say that EH, which is the Hall field, is equal to minus 1 upon Ne into Jx Bz. Jx Bz. Okay. So this is the Hall field. So what does it mean? It means that Hall field, which is internal field of the specimen, which is produced due to the external Lorentz force, is what? Is proportional to the applied current as well as the applied magnetic field, right? So the Hall voltage produced or the Hall electric field produced is proportional to the applied electric field and the applied magnetic field, and this is known as the constant of proportionality, right? So this constant of proportionality, it could be replaced by a constant known as the Hall coefficient, right? And its value is minus 1 upon Ne. Okay, so here we have replaced this constant by a coefficient, by Hall coefficient, and the value of Hall coefficient is minus 1 upon Ne. Okay, so and you can see that its value is equal to EH upon JXBZ. From this equation itself you can see, if you want to find out the value of minus 1 upon Ne, this is equal to EH divided by Jx upon Bz. Okay, so this is the Hall coefficient. This is called RH is called Hall coefficient. RH is called Hall coefficient. Okay, let us talk about the unit of Hall coefficient. कई बार एग्जाम में पूछा जाता है एक नंबर के क्वेश्चन में कि what is the unit of Hall coefficient. So the unit of Hall coefficient is electric field का unit, which is voltmeter divided by ampere, and the unit of magnetic field is Weber per meter square. So this will come out to be volt meter cube per ampere per Weber. So this is the unit of Hall coefficient. Now let us talk about the mobility, right? This experiment can also help you to find out the mobility of the charge carriers, right? How to find out the mobility? Starting with, we know that Jx current density is given by NeVx, ignoring the minus sign because it is just giving you the information about the direction. Okay, so Jx is equal to NeVx. We also know that Jx is equal to sigma x Ex, where sigma x is the conductivity of the metals. So we can say that sigma x is equal to Jx upon Ex, which is equal to, putting the value of Jx from here, so this is NeVx divided by Ex. Okay, so this value Vx upon Ex, you can also say that the drift velocity produced for unit electric field, right? The drift velocity produced for unit electric field is called mobility. That is mobility. It is denoted by mu h, and its value is Vx upon Ex. Okay, this is called this is for electric field is equal to 1 voltmeter. ओके, तो जब इलेक्ट्रिक फील्ड 1 वोल्टमीटर होगा तो उस टाइम पे जो वेलोसिटी होगी इलेक्ट्रॉन्स की, दैट इज नोन एज द mobility. That is called mobility of the charge carriers, right? So if you put this mu h in this equation, then sigma x is equal to Ne mu h, or you can say that mu h is equal to 1 upon Ne into sigma x. In general, if we are talking in 3 dimension, then mu h is equal to 1 upon Ne into sigma. Sigma is the conductivity. Okay. So what does you conclude from this article? What does you conclude from this experiment? Suppose if you are doing this experiment in the laboratory, so this can help you to determine, number one, the sign of charge carriers. Sign of charge carriers. If the sign of Hall coefficient is negative, it means that the charge carriers are electrons. If it is positive, then the charge carriers are holes. Number two, it helps to determine the number of charge carriers. Number of charge carriers. Means N. Then charge carriers per unit volume. Unit volume के अंदर कितने charge carriers हैं? So the concentration of electrons or the concentration of holes you can determine per unit volume using this experiment. Then mobility of, it helps to determine the mobility of charge carriers. Mobility of charge carriers, right? So this is the importance of Hall effect. Yeah, is it clear? Any doubt here, students?
No, ma'am.
Okay, great. So the last article of this chapter is magnetoresistance.
Ma'am, I think enough for today, ma'am.
It will just take 3-4 minutes, not more than that. So I just wanted to complete this chapter at least. So and we have time also. So I think just it will take 2 minutes, not more than that. Okay.
Okay, ma'am.
Yeah. So magnetoresistance. Okay. So the magnetoresistance of a crystal uh, refers to the change of electrical resistance of a crystal when a magnetic field is imposed. Okay, if a crystal is kept inside the magnetic field, then how the resistivity of this crystal is changing, how the rho is changing, so that talks about the magnetoresistance, right? So this effect is due to the fact that when magnetic field is imposed, the path of the electrons becomes curved. As you see, as you saw in the Hall effect, that if this is the path of the electron under the influence of the magnetic field, the path becomes like this, right? So as a result, because the path of the electrons is changing, so as a result, there must be the number of collisions inside the system might be increasing or decreasing, or the randomness of the system increases, right? So as a result of this, the resistivity, the resistance of the crystals changes, right? So due to the change in the path of the electrons, since it becomes curved and do not go exactly in the direction of the superimposed electric field, the resistivity of the metals changes. Okay, and in case of metals, the resistivity increases. So the magnetoresistivity is given by change in the resistance divided by resistance without field. So here rho naught is the resistance without magnetic field B, and delta rho is the change in the resistivity in presence of magnetic field and in the absence of magnetic field. Okay, so this is the change in the resistivity, and rho naught is the resistivity at no field, when there is no magnetic field. ठीक है, इसके लिए एक्सप्रेशन होता है डेल्टा रो अपॉन रो नॉट is equal to alpha B upon rho naught square divided by 1 plus gamma B divided by rho ka square, where alpha and gamma are constants. Alpha and gamma are constants. Rho naught क्या है? Resistivity without magnetic field. And what is rho? Rho is the resistivity with field. Yeah, is it clear, students? Any doubt? Any doubt,
No,
students?
ma'am.
Okay, great. So this is all for the module number 1, transport properties of materials. And with this, we are completing the first chapter of your syllabus.